Given that the density of steel is 7.8 times 10 to the 3 kilograms per meter cubed, what is the buoyant force on a 100 kilogram block of solid steel submerged in water? So we're talking about, if this is, say, the bottom of, I don't know, a pond or a lake or something, maybe the ocean. Somebody threw in a block of steel and it's sitting here on the bottom. It sank. And it turns out the formula for the buoyant force that we started with at the top of the key concepts page, which is really the general formula, kind of works for all cases. We can use that one here. I also gave a more specific formula for this particular case, and I'm going to hope to be able to see how that ties in with this formula. Now, in this case, since this is in water, I think this row, which was really the row of the fluid on the key concepts page, but in this case, the fluid that's relevant is H2O, so I'll put a little H2O in there. This volume was the volume of fluid displaced, but in this case, that is also the volume of this object since it is completely submerged. Now, density of steel, let's say, in this case, would be equal to the mass of steel that we have here divided by the volume of steel. And so that implies that that volume, this is I'm thinking about this like the volume of the object, and in that sense, this mass M here really is the 100 kilograms that we're given in this problem. But in terms of that, I can cross multiply and say that volume would be equal to mass divided by the density of steel. So if I take that and substitute that into this expression, what would happen? I'll get mass over density of steel here. And then maybe I can rearrange things a little bit here and see that it is density of H2O over density of steel. And then this is G and M here, right? But I can rewrite that as mg, which is clearly equal to the weight. And so the formula that we had on the key concepts page was like rho of the, it said fluid there, this one's H2O, right, for this specific situation, divided by rho of object, which in this case I said is the density of steel, multiplied by the weight of the object. So that was the formula again on the key concepts page, but maybe specific to this scenario. So we've seen how that can come from this general formula for a situation like this. To actually solve this, though, maybe I can use this expression right here, since we know that it's 1,000 kilograms per meter cubed for water. Let me make that cube look a little better. And the density of steel we're given at 7.8 times 10 to the 3 kilogram per meter cubed. And let me go, it's going to be multiplied by 100 kilograms times 9.81 meters per second squared. And so now I can go to my calculator to do all that. 1,000 divided by 7.8 times 10 to the 3 multiplied by 100 times 9.81 gives me 125.769238, which in this case, I don't know, maybe I could round that off to about 130 newtons, or maybe it's 126 if we don't follow sig fig rules, right? Let's see how it lines up with what the slide says. Well, I guess the slide with 126 went with 126 newtons. So obviously when I wrote this slide, maybe I failed at implementing appropriate significant figure rules. So definitely keep this one secret from the rest of the science department, okay?